There is this one system that is used in almost every single game. It's what allows you to create these smooth, flowing paths in Planet Coaster, helps guide the player through cinematic moments in Red Dead Redemption 2, and is what helps make the camera of God of War so immersive. The system I am talking about is called splines. And it all has to do with this simple line. At their core, splines are incredibly simple. It's basically just a smooth path. It can be used to draw tracks to allow a set of cards to follow it, and potentially ride the player into a scary cave. Or maybe it can be a road that allows the player to drive through the game world. It allows for building more complex things too. Instead of a road, it can be a giant water slide, ending in a lake. Hello there, my name is Lucas and welcome to Vlog. In order to explain how to create paths like this, I'm going to have to take a step back. I'll start out by drawing 2 points and connecting them with a line. I'll introduce a function called lerp, which is short for linear interpolation and returns a point on the line based off of value t. This value can lie anywhere between 0 and 1. The function allows us to gradually move a third point between points A and B. When t equals 0, we're exactly at point A. When t equals 1, we end up at point B. Any other value will get you somewhere in between, as you can see in this animation. Now let's introduce yet another point. Now we have 2 lines, one between point A and B, and one between B and C. We will perform the same lerp operation on both of these lines, using the same t value. This gives us 2 new points, each moving along their respective lines. Something interesting will start to happen when we form another line between those 2 new points, and perform the same lerp operation. As we slowly increase t from 0 to 1, you'll see that the final point no longer moves in a straight line. Instead, it starts to trace out a curve. And just like that, we've created a smooth path using nothing but a few points and a simple function. Now let's take a step further and add yet another point. We'll repeat the same process. We lerp on all of the lines, giving us some points, lerp again between those points, now trace another line between those points until we have our final point. What we are pretty much doing is just keep lerping stuff until we have nothing left to lerp. Now if we gradually start to increase t again, we can see that it traces out this smooth curved path for us. We can even make adjustments to the path by grabbing one of the points and moving it around. Notice how the path ends at point A and D. We call these anchor points. Do you also notice that the path does not cross B and C at all, yet still seems to be affected by it? These points are what we call control points and allow us to control the curvature of the path. What we are now looking at here is a spline. But more specifically, this single curved section is called a spline segment. And the nice thing about segments is that we can chain them together. To extend this path, we need only 3 new points. By sharing the last anchor point of one segment with the first anchor point of the next, both segments meet at the exact same position, resulting in a smooth, continuous path. We can pretty much keep doing this and make the path as long as we want to. And with that, we've gone from a single line to a smooth, editable spline. So far, splines look pretty great. We can interpolate between 2 points in order to shape curves and chain those segments together into long, continuous paths. But there's a problem hiding under the surface. Let's say I want to move an object along this spline. The obvious thing to do is increase t over time, and at first glance that seems like a perfect solution. But watch closely. Even though t increases at a constant rate, the object does not. Sometimes it speeds up, sometimes it slows down. The reason for this is simple. Our parameter t does not represent a distance, it's just a parameter used to evaluate the curve. Equal steps in t do not correspond to equal distance along the spline. To make this more obvious, I'll draw a few points along the curve and put them at equal increments of t. Notice that the points around the center lie closer to each other than the points at the outer part of the spline. This uneven spacing is exactly why motion along the spline feels so inconsistent. And this issue doesn't just affect movement. It also makes it difficult to determine the actual length of the spline. So how do we deal with this? One way to solve this is to sample the spline and place points along it at equal distances. Let me show you how it works. Suppose we want the points spaced at 25 units apart. We start by evaluating a new point on the spline by increasing t by a small amount. Next, we measure the distance between this new point and the previous one, which initially is just the start of the spline. In this case, the distance turns out to be 30 units, which is more than the 25 we were aiming for. Since 25 is roughly 17% less than 30, we move the new point about 17% back towards the previous point. And that's it. We simply repeat this process over and over until we have a set of points evenly spaced along the spline. One drawback, however, is that it's an approximation. The points don't lie perfectly on the curve itself, but in practice it's close enough and will do just fine. If we now go back and move the object along the new line we created, we can see that it finally travels at a constant speed. Problem solved. Now on to the next thing. I've created this small platformer game where the player has to climb on top of this mountain. We could keep this simple and just mount the camera somewhere behind the player, and honestly, that would work. But what if we wanted to make the camera more dynamic? To move through the scene as the player progresses and review the environment in a more interesting way. This is where splines really start to shine. What we can do is introduce two splines into the scene. The first spline represents the player's path. It's laid out roughly along the route the player is expected to take as they climb the mountain. As the player moves, we continuously find the closest point on this spline to their position. This gives us a stable, one-dimension representation of where the player is in the level, regardless of how they jump, fall or move in this 3D space. Now for the second spline. This spline is called the camera spline. Instead of attaching the camera directly to the player, we can place it on this separate spline. The key idea is simple. The position of the camera on the camera spline is driven by how far the player has progressed along the player spline. And this is where things get interesting. Because now, the camera no longer reacts to every small movement the player makes. It reacts to progress. It allows us to carefully choreograph camera motion, pulling back to show scale, sliding around corners, or revealing upcoming areas at just the right moment. All without writing a single hard-coded camera transition. Pretty cool, right? There's one final thing I'd like to show you. So far, we've been using splines to describe motion, moving objects and controlling cameras. But splines aren't just useful for movement. They can also be used to create geometry. Instead of treating a spline as something invisible, what if we turned it into something solid? Something you can actually walk or drive on, like a road. Or something water can flow through, like pipes or water slides. Let me show you how to generate meshes from splines. It might sound complicated at first, but the basic idea is actually quite simple. We'll start off with the simple road mesh. Our final goal is make it take the same shape as the spline over here. The road mesh is currently just a straight strip. If you're unfamiliar with meshes, meshes are made out of a bunch of points, called vertices. These vertices are connected to each other in order to form these triangles, which the game engine then renders for us. Meshes are basically just a bunch of triangles made by connecting vertices. Now how do we form this straight road into the shape of the spline? To do that, we'll use a technique called mesh deformation. Before we modify the mesh, we first need something from the spline. For every point along it, we calculate a direction vector, also called the tangent. This tells us which way the spline is pointing at that position. Then using that tangent, we can calculate the right vector, which tells us which way is sideways relative to the curve. I'll visualize those right vectors using these yellow lines. Now here's the key idea. Each vertex in our road mesh has two important pieces of information. How far it lies in the forward direction and how far it lies to the left or right. For each vertex, we determine how far along the spline it should be placed. We evaluate the spline at that position to get a point in that space, then move that point sideways using the spline's right vector, scaled by the vertex's original horizontal effect. In other words, we take the spline position, add a sideways effect, and move the vertex to that new position. And once we do this for every single vertex, the flat strip starts to bend. Now we simply copy this flat strip a bunch of times and repeat the process until we've fully covered the spline. And suddenly our straight mesh segment becomes a fully curved mesh that follows the path of the spline. That's all I have to tell you about splines for today. There's still much to discover, so don't refrain from trying this stuff out yourself and learning what other cool things you can do with this. I want to wish you a good morning, afternoon, evening or night, and see you in the next. Goodbye.